All right, so to start our lesson on exponential functions, we're kind of flipping the class today. Usually I do some lecture and then let you try things in your groups. Today you're going to work in your groups on this little activity. No, I'll get it to you for you in a second. On this little activity about rabbits, 2 different rabbit populations, and we're going to use that to motivate what we're learning about in class today. Okay, so I want you to, in your groups, do the front and back of that first page, and then we'll discuss it in 10, 15 minutes or so. Results? Okay, so in our 2 models, the first one is linear, 1,000 plus 1,000t, and that's the one where we increase the population by 1,000 rabbits every year. And we know it's linear because it has the form y equals mx plus b. And it has a constant rate of change, which is the definition of a linear function. And the other one, its formula was y equals 1,000 times 2 to the t. That's called an exponential function, okay, when you're constantly multiplying by the same number to get from year to year. So in the first equation, in the linear equation, what does the 1,000 mean? The first 1,000, this one, the starting population. And what does it mean in the exponential model, the first 1,000? Who does it represent? Same. This is also the starting population. So what is the effect of the second 1,000 in the linear model? What does that 1,000 represent?
Every year.
Yep, so we could call that the growth rate. Growth rate of 1,000 rabbits per year. And then what's the effect of the 2 in the exponential model? What does this 2 represent?
It's doubling every year.
It's the doubling. Yeah, so doubling means times 2, right? So the 2 in the exponential model represents a growth factor. So we call it a growth factor because it's what you multiply by. Factor is the word you use to represent one of the terms in a multiplication problem. So we call it a growth factor as opposed to a growth rate that we use for linear. But they both govern growth, right? So the 1,000 represents the initial number of rabbits, and then in the linear model we have a growth rate, and in the exponential model we have a growth factor. So when you graphed the rabbit population using the exponential model, you should have gotten something like this. What is the y-intercept of the p of t equation, 1,000 times 2 to the t? 1,000. Yep, because in general, to find y-intercepts, you plug in 0, make x 0. So we have 1,000 times 2 to the 0. Anything to the 0 is 1, so this is 1,000 is the y-intercept. And you can see it on the graph. Y-intercept of about 1,000. So we have something in this graph called a horizontal asymptote. It's a horizontal line. An asymptote is just a fancy word for a line that the graph gets very, very close to, but never hits. So is there a horizontal line in this picture that my graph gets very, very close to, but doesn't touch the x-axis? Or if I wanted to give an equation, it would be the line y equals 0. How do you know that it never touches? How do you know that it never touches the x-axis, that it just gets really, really close? Yeah, there's no number I can raise 2 to get 0. If I try to solve 1,000 times 2 to the t equals 0, try to find places where this equals 0, there isn't any. I could divide both sides by 1,000, and I'd get 2 to the t equals 0. And then I'm thinking, okay, if I raise 2 to any positive number bigger than 1, like 2 squared or cubed or to the 4th, I'm just going to get a big number. If I raise to a fraction, like 2 to the 1/2, that's square root of 2. To the 1/3 would be cube root. So I'd be taking roots of this thing, which will never be 0. And if I raise to negative numbers, if I raise 2 to a negative number, you just take the reciprocal and raise to the positive. So like 2 to the negative 2 would be 1 over 2 to the positive 2. And those will give you fractions that get smaller and smaller and smaller, but never 0. So this has no solutions. So that's how I know it never touches the x-axis. But it does get very small. It does get close to 0. All right, so the definition of an exponential function is a function that has the form a times b to the x. And I have some restrictions on the base b, and that b has to be positive, and it can't be 1. B has to be positive, and it can't be 1. So I want to figure out, like, why do I have these restrictions on b? So first, let's imagine what would happen if b equaled 1. Then my function would be y equals a times 1 to the x. And what's 1 to the x? 1 to the anything is 1. So this should be a times 1, which is a. So if b equals 1, this is just a constant function. It's just a horizontal line, which is not exponential growth. Okay, so that's why we rule out b being 1, because it's not exponential growth. It's just a line. Now, what would happen if b were negative? So maybe I'll just pick a value for b that's negative, like negative 2. I would have y equals a times negative 2 to the x. It's going to turn positive sometimes, right? When's it going to be positive? When the exponent's even. And when the exponent's odd, it's going to be negative. So I'm going to get a graph that ends up looking like that, which is not the exponential growth that we're looking for. We're looking for just a straight growth. This is growth and decay and growth and decay. So that's not what we want. So we say b can't be negative.
Is there a name for that?
That would be an oscillating function with increasing amplitude. But you won't study that till you take pre-calc. All right, so we really only have 2 flavors of graphs that represent exponential functions, growth and decay. Okay, so growth happens when the base is bigger than 1, and decay happens when the base is a fraction between 0 and 1. Big base, you get growth. Little base, you get decay. We call the base either a growth factor or a decay factor. So in our rabbit population, which is this model here, this 1,000 times 2 to the t, the base is 2. It's bigger than 1, so we know we have exponential growth. And 2 we call the growth factor. What describe the rabbit population that this equation would model? If that was representing a rabbit population, describe what's happening to it. They're dying. Yeah. Can you be more specific? by a half each year. We start with 1,000 and they're dying off, half of them die off every year. So this one is decay and the function is heading towards 0. All right, so here I've picked 2 random examples of the different flavors of exponential functions, a 3 to the x and a 1/3 to the x. And we're just going to go through and answer several functions that we have come to ask about functions. Domain, range, is it 1-to-1? Does it have any extrema? What's its end behavior? So these are typical questions that we've been asking of all the functions we study. Now we're going to look at the answers for the exponential. So there are arrows on here that aren't shown. So we might need those when we do end behavior. All right, so let's just look at the blue graph first, the exponential decay function. What is its domain? What x values does it live on? Or that is, what x values are you allowed to plug into the formula? Anything. I can raise 1/3 to any power I want. Yep. And it appears that my blue graph lives on all x values if the arrows keep going in the direction they're pointing. So my domain for the blue graph is -infinity to infinity. How about the range for the blue graph? What y values does it live on? Zero to infinity. It doesn't go below the x-axis. So my range is 0 to infinity. Do I include 0? No, because we talked just a minute ago about how there's no value I can raise 2 to, or any number 2, that will give me 0. So I have an asymptote at 0. Don't include it. The blue graph, is it 1-to-1? Does it pass the horizontal line test? Yes. That makes it 1-to-1. That is an important question because it tells us that this function has an inverse. This function has a function that will undo it. All right, how about any extrema? Does the blue function have any extrema? Nope, no maxes or mins. And end behavior, I have to describe the behavior at both ends. So I'll say as x approaches infinity and as x approaches -infinity, what happens to y? So as x approaches infinity, as my x values go really far to the right, what happens to the y values on this graph? They go to 0. As x goes to infinity, the y values approach the x-axis. We've never actually looked at end behavior that does anything but go to plus or minus infinity, so this is something new, to have the end behavior approach 0. As x approaches infinity, y approaches 0. And then as x approaches -infinity, what happens to the y values on the blue graph? They go up to infinity. Does this make sense? Okay, so let's do the same questions for the pink graph exponential growth. What's its domain? Same. -infinity to infinity. It lives on all x values. And its range? Same. It lives on 0 to infinity. For y, x-axis up. Is it 1-to-1? Yes, passes the horizontal line test. It doesn't. Round brackets don't include 0. I mean, aren't included. Square brackets are the ones that include. No extrema. Just like the blue graph, no extrema. And then the end behavior for the pink graph is the same as the blue graph, but reversed. The ends are the opposite of what they were here. So I would say as x goes to infinity, y goes to. As x goes to negative infinity, y goes to what? So as x goes to positive infinity, what happens to the y values on the pink graph? As x gets big, y also gets big. So this goes to infinity. And as x goes in the other direction, as x heads towards negative infinity, what's happening to my y values? They go to 0. So an asymptote is end behavior that approaches a constant, right, as opposed to infinity. Have an asymptote. Yep. We'll do some examples at the end where it's not 0. They just have 1. They just have the horizontal asymptote that it approaches. Like that. That's not an exponential. But you can have a graph that looks like that. But that's not an exponential function. Because exponentials have domain negative infinity to infinity. So you can always plug in something from the other side. All right, so we are looking for functions of the form a times b to the x, whose graphs are shown. So we know a, from our rabbit example, we know that that first number is the y-intercept, right? It was the 1,000 and the 1,000 times 2 to the t. So a is the y-intercept, and b was the growth factor. So this exponential growth is pretty similar to linear, right? In terms of how to make the equation. It's built from the starting point, the y-intercept, plus a growth rule. In linear, the growth rule is a consistent amount that you always add. In exponential, we have a growth factor, which is a consistent number you always multiply by. So if I were to mark my y-intercept there, what does that look like? 1. Okay, so I would have y equals 1 times b to the x. Now I just have to figure out what b is. So I went from 0, 1, so I make a little table here, x, y. I have 0, 1, and then I have 2, 25. And I skipped over 1. I don't have any information for 1 here. And what I want to do is figure out what is my multiplication factor. What am I multiplying by to get from term to term times something times that same thing? What can you multiply 1 by twice to make a 25? You would add 12.5 twice, right? So if I was going to add the same amount, 5. If you multiply times 5 times 5, that's how you get from 1 to 25, by multiplying by the same number twice. So my growth factor has to be 5. So I have y equals 1 times 5 to the x, or just 5 to the x.
In this case, it's 2. What's squared is 25.
So you can write a little equation if you want. You could say 1 times what squared is 25. And b squared equals 25. B has to be 5. And I throw away the -1 because we already said the base can't be negative in an exponential growth. Great, good. Because that's the y-intercept, yep. Mm-hmm. Yep. Yeah, so here I'm going to write down a times b to the x, right? That's always your general form for exponential. Here I'm going to replace the a with a 3 because that's my y-intercept. And then I just have to figure out what b is. What do you multiply by? I make a little xy chart here. I have 0, 3, and 1, 6, and 2. I gotta scroll up a little bit. 2, 12. So what does it look like my growth factor is? What am I multiplying by? As x goes up by 1, what am I multiplying the y's by? 2. So my b has to be 2. So I have y equals 3 times 2 to the x. I think I'm going to make up one more for you to try on your own. Oh yeah, plenty of time. Okay. All right. Find an equation for this exponential function. So this is the point 2, 9. All right, so let's discuss this. So we know it's exponential, so it's going to look like y equals a times b to the x, right? We know it's exponential just because I told you, right? I didn't write it down, but that's what we're doing today, so exponential. A is your y-intercept, so you can immediately plug in 4 for a. Okay, then we have to figure out what is the growth factor. So to find the growth factor, there's a couple of different approaches. I'll show you a couple. So the one I particularly like is to make a little table, and I'm trying to find that constant growth factor that has me start at 4 and gets me 9 at 2. So I didn't tell you anything about the value at 1. If you had known that one, it would have been easy to figure the growth factor because you would just say 4 times what gives you this guy. All right, but I didn't give you the value at 1, so you say, well, because this is exponential, I'm always multiplying by the same amount. As x goes up by 1, your y's change by a constant growth factor, which we call b. So what this little table says is that if I start with 4, I want to multiply by b twice. What should b be? So that I multiply it by it twice and I get 9. So this says 4b squared equals 9. And then you solve for b and you get 3/2 or 1.5. So we've got the growth factor b. Another way to think about it is like with function notation. So if you go back over here, y equals 4 times b to the x. Well, I know the point 2, 9 has to make this equation true. So if I plug in 9 for y and 2 for x, because the point 2 comma 9 is on the graph, I end up with the exact same equation as I did when I did my little table thing. So you have 9 equals 4b squared, and you get b has to be 3/2. So my equation is going to be y equals 4 times 3/2 to the x.
Might not give us 0, 1, 2, might give us
I might give you like 0, yeah, or I might give you 0 and, 3.5. Yeah. Okay with this? Okay. All right, so the way you can tell just by looking at a table whether or not it's exponential, if your x's all go up by 1, your y's have to change by a constant factor. That's all. So you just look at, is there a constant factor that gets you from term to term? In this case, there is. It's times 2. So if I wanted to write the equation for this guy, I would write y equals a times b to the x. What's my y-intercept? 3, because when x is 0, y is 3. So you can get y-intercepts from a table as well. B is the constant factor, which in this case is 2. This is actually the exact same problem that we found the formula for 2 problems earlier. It's just that I gave it to you in a graph that time, and this time I gave you a table. All right, lastly, we have a new kind of parent function, y equals a to the x. 2 to the x or 3 to the x, we can treat those as parent functions and make transformations of them. So if my blue graph in each of these 3 pictures, the blue line represents y equals 2 to the x, and the pink line is some transformation of it. So we're going to try to, 1, state what the transformation is in words. Okay? And then 2, try to take that statement and change the equation to make it match it. So if we look at the blue curve and the pink curve here, what transformation seems like it has taken place? Don't jump right to the equation. That's good. But just, it's a mirror image over the x-axis. Yeah. So we have a reflection over the x-axis. Okay, so then Ayana was saying that has to, when you have reflections, you put negative signs into the equation. When it's over the x-axis, where am I going to put the negative sign? Am I going to change the input x or the output 2 to the x? The output. You got it. So here I'm going to have y equals negative 2 to the x. I did. I haven't broken that rule. That's a really, really good question. So I wrote y equals negative 2 to the x, but I said earlier, you can't have a negative base. Have I broken the rule about having a negative base here? Yeah. Y equals negative 2 to the x. Unless I have parentheses around the negative 2, that means y equals negative 1 times 2 to the x. So it's not the 2 that's negative. The negative is outside of the whole thing. So if you want to be really clear, you could go like this, if that helps you think about it. Saying that negative is outside of the 2 to the x. But you don't need it because the order of operations says I'd have to do the exponent before I deal with the negative. Okay, let's look at the next one. I have y equals 2 to the x in blue. Just in words, what appears to have happened? What transformation took place from the blue to the pink? Well, there's several ways we can think about it. So I have, I could think of it as a vertical shrink. a horizontal stretch, and the only one that I just heard that it is not is a vertical shift. Because if it was a vertical shift, the whole thing would have had to move up and down, which means my asymptote would have moved, right? So if I had shifted the blue graph down, my asymptote would have shifted down also. So I can rule out vertical shift. It could be a horizontal shift where I shifted the whole thing. Let's see, my y-intercept moved right 1. So I could write this as a horizontal shift right 1. I could write it as a vertical shrink. Without more information, it's really hard to tell exactly what happened because I don't have lots of point values. So I could say y equals 2 to the x minus 1. I could say y equals 1/2 times 2 to the x. Either of those would explain what happened to this point. So this used to be 1. If I multiply by 1/2, it would bring it down. Shifted it right, it would land over here. Right, in this last one, remember the original's in blue, transformations in pink. This time, the asymptote moved. Right. The pink line approaches this dashed line as opposed to the x-axis. So what do you think, what transformation do you think happened? Vertical shift, up 1 unit. So this would be y equals, how do you represent a vertical shift up 1 unit? Just add 1 at the end. So this would be 2 to the x plus 1. Great. Any questions so far? All right. So this is a little bit of a short class. At the end of your previous packet is the study guide for test 3. So you can pull that out and we can start working on that in your groups and I will come around and help. Do the what? What are you talking about?